Hello everyone, my name is Abhishek and welcome back to my channel. In today's Zero to Hero tutorial, we will learn about Kubernetes Event-Driven Autoscaling, or also known as KEDA. KEDA is a very important concept, especially if you're working on Kubernetes or if you're dealing with scaling on Kubernetes. And just like any other Zero to Hero tutorial, I prepared a detailed GitHub repository. So after watching the video, you can just check the link in the description and then you can revise the topic that you have learned. The GitHub repository also covers the demonstrations that I'm going to perform. So without wasting any time, let's get started and please make sure you watch the video till the end. Let's start with absolute basics. We'll definitely understand what is Kubernetes event-driven autoscaling. But before that, let's understand what is scaling and why is it important at all. Imagine there is an e-commerce platform, a DevOps engineer working for the e-commerce platform. DevOps engineer tries to understand about the platform. The maximum requests that this platform would get at once are 100. So maximum orders what are placed on the platform at once are 100. But the orders microservice could only handle 60 orders at a time. Now what DevOps engineer would do to tackle this situation? Probably would deploy two virtual machines, orders microservice on two different virtual machines, and front face this with a load balancer. Now, whenever user tries to place an order with the platform, request goes to the load balancer, and load balancer would balance the request between two different order microservices. If there are 100 requests at a time, load balancer would place 50 requests here and 50 here. If the requests are 80, it's even more easy. Probably 40 goes here and 40 goes here. But what if the e-commerce platform runs a sale? Imagine this platform has never run a sale. Now they started running a sale and unexpectedly, the number of orders that are placed at once have reached 150. Now in this case, what would happen? Load balancer would still try, but eventually the platform would go down, or maybe the users would experience a bad user experience. How DevOps engineers would tackle this scenario? Immediately, they would add a new virtual machine and deploy a new orders microservice to it. If DevOps engineers already know there is a sale, probably they would do it beforehand. And this process is called as scaling. But this is a manual process. If the same process is done automatically, we call this as autoscaling. That's it. Now, what is the advantage of autoscaling? Imagine during the sale, you must have expected 150, but the number of users, probably the sale that is running on the platform is super successful, and the number of orders concurrent have reached 300, double of what is expected. Manual scaling would still fail in that case, but autoscaling wouldn't. Because what autoscaling does, as soon as the request goes to 150 or maybe 160, it would add a new virtual machine and deploy orders microservice to it. Further, it would deploy one more virtual machine and attach all of them to the load balancer. So that's why autoscaling is very important. And how autoscalings work? Basically, they rely on a trigger. Now, they need to know, or you need to tell the autoscalers when to add a new virtual machine. It can be metrics like CPU utilization or memory utilization. For example, in this case, you can say, hey, autoscaler, whenever the CPU utilization on the virtual machine, see, eventually if the virtual machine or orders microservice in it is processing the orders, the CPU on the VM would go high. So you can tell if the CPU utilization goes to 80%, add a new virtual machine. Or if the memory utilization goes to 80%, add a new virtual machine. In fact, in the modern autoscalers, you can also rely on the custom metrics. So you can basically take a metric from your Prometheus configuration and you can say, hey, autoscaler, rely on this custom metric, act upon to it. Now this is nice, right? Autoscaling as a concept is very good. But what we learned here is on the virtual machines. Today, everyone, most of the companies are working with Kubernetes. So they are using Kubernetes as a target platform for their traditional applications, machine learning workloads, AI, LLMs as well. So is there auto-scaling concept in Kubernetes? Yes. Out of the box, Kubernetes supports something called HPA, horizontal pod autoscaler. Now this is an autoscaler. What it does, as the name suggests, it would scale the pod resources in Kubernetes. Now if we take the previous example, again the same thing, e-commerce platform where DevOps engineer, instead of deploying virtual machines on the Kubernetes cluster, what DevOps engineers would do, they would deploy the orders microservice in pod, a deployment with 2 replicas probably. And HPA, whenever there are more orders on the platform, maybe during the sale or maybe during the peak hours, would bring the pod count to 3, pod count to 4, pod count to 5, whatever is required. And Abhishek, what are the triggers that horizontal pod autoscaler would act on? Same triggers, no difference. This is also an autoscaler. It can also trigger on CPU utilization. It can also trigger on memory utilization and custom metrics from Prometheus, whatever you would like to configure. So just define a manifest file in Kubernetes, right? Along with your traditional deployment, you can deploy HPA and you can define within the HPA, or you can define within the HPA configuration. Whenever CPU utilization goes to 80%, 70%, whatever it is, increase the pod count. The best part about HPA, you can define what is minimum and what is maximum. Abhishek, why is it important? Let's say for some reason there is issue with your microservice. Your microservice is unnecessarily using the CPU resources. If it is a Java application, it is very common. There can be a memory leak, and the memory leak might be consuming a lot of resources. Now, in that case, overnight, your platform might spin up, or HPA might spin up 100 pods if there is no limit, or you haven't configured the maximum. And if the pod count is going to 100, what is the major problem? The compute. So you have to pay for the compute. If your Kubernetes is on AWS, AWS would charge you for 100 pods, but most of your pods are idle, or most of your pods have scaled because of some issue within your Java application. So as DevOps engineers, what you do, you configure minimum and you configure maximum. So you can say 2 as minimum pods and 10 as maximum pods. After 10, it's okay to fail. Or maybe you can set maximum to 20 and minimum to 1. But you cannot set minimum to 0. So this is one limitation with HPA. You cannot scale down your pods to 0. Maximum that you can do is 1. So Abhishek, this is good. Then HPA is amazing on the e-commerce platform. Whatever the example that we have taken, along with deployment, we will configure HPA as well as DevOps instance, and everything is taken care by it. Of course, yes, but there are 2 major disadvantages with HPA, right? What are these 2 major disadvantages? 1, HPA can only rely on the metrics. It cannot act upon the events. I'll explain in a minute. The second disadvantage, HPA cannot scale to 0. What is the problem? Scaling down to 0. Why is it important? Let's start with understanding this first. So let's say, not an e-commerce platform, or maybe you're working for a banking application, or even e-commerce platform is fine. In your banking application or in your e-commerce platform, there can be 500 microservices. Right? A platform is not made with a single microservice. There can be 500 microservices. Now at 2 a.m. in the night, all of your microservices might not be active. Probably, if you take orders microservice at 2 a.m. in the night, nobody might be placing an order. Or maybe at 2 a.m. in the night, nobody might be placing a payment. Nobody might be logging into your banking application. Then what is the point of running the pods for it? Okay, out of 500 microservices, 300 microservices might be important for you, or 495 microservices might be important for you. But the 5 microservices, it is okay for you if there are no users to bring the pods to zero count, or basically to stop the pods, have zero replicas of it. Because if the pods are active, the underlying platform, it can be AWS, it can be Azure, they would charge for the compute. So as long as they are running, the platforms would charge you for the compute. This is where KEDA comes into picture. KEDA can scale your pod count to zero. If nobody is using it, you can just say, or KEDA automatically takes the decision where it pulls your pod count to zero. And as soon as there are users, okay, whenever there are users or whenever the service needs to be active, it will automatically bring the pod count to one. And it is an automatic process. This is one advantage. Now, the second advantage is very, very important. I'll explain you this with an example because it is easy to understand. Imagine the same e-commerce platform, but this time let's go little deep into it. E-commerce platform selling some merchandise online. So users would log into the platform through the user interface or typically internally with the API and place orders to the e-commerce platform. Now what happens internally? Whenever users place order, it's not that one user would place the order. Thousands of users can place the order. So all the orders would go into a queue, right? A queue where order 1, order 2, order 3, order 10, all of them are placed. Now there is an orders microservice which would read the orders from the queue, the first come, first serve, right? Read the orders from the queue and start processing the orders. This can happen async most of the times. Probably it would take one order, asynchronously perform the payment process, the shipment process, and process other orders as well. So this is the typical flow. Orders would go to the queue, which is basically event. Events would go to the queue, and order microservice would process the events from the queue asynchronously and execute the required actions. It can be payment or the shipment. Now, within this case, imagine the e-commerce platform is Amazon, and Amazon runs something like Cyber Week sale. And during Cyber Week sale, what Amazon, or during the Black Friday sale, what Amazon does, all of a sudden, you would see a big sale on a random product. You don't know when the user count would be more. It's not that typically they would run offers all the time. Of course, they would do, but they would run some big flash sales. All of a sudden, you see iPhone price dropping down. Maybe they might have only 1,000 iPhones. So they would launch a flash sale maybe at 6 a.m. in the morning or 7 p.m. in the morning. You are not at all sure about it. Now what happens in that case? Suddenly the order queue will be filled. Probably one person would watch that there is a sale and would post on a Telegram channel or would post somewhere, and all of a sudden the queue is filled up. Imagine in this case, the DevOps engineers have set up HPA. This would lead to a bad user experience. Why? Because HPA is not at all looking at the queue. What happens? In this case, let's say there are two orders microservices. Okay. When HPA would work, HPA would only work, or it would only act if the CPU utilization on this orders microservice, let's say, is configured for 80 CPU as threshold. Once this 80% is hit, another orders microservice is added. Another microservice is added. Another microservice is added. Of course, HPA can address the problem, but by the time the orders microservice start processing the queue, and from 20, let's say the CPU utilization is only 20% initially, the queue is filled up. What this service does, it picks up one element from the queue or maybe two elements from the queue. CPU would go to 30, then it would go to 40, then it would go to 50. Eventually, when CPU goes to 80, only then HPA would add, and HPA would add one more orders microservice, or maybe it would add 10 more orders microservice. But during this time, there would be a bad user experience. I'm not saying this would take 15 minutes or 20 minutes. No, it would typically take some seconds or minutes of time. But during that seconds or minutes of time, there would be bad user experience. Imagine the same thing with uh, maybe a platform that is running cricket. Maybe a very good batsman like Virat Kohli boxing, or a platform running show like Game of Thrones. All of a sudden, there would be spike. All of a sudden, there would be a queue that is completely filled up. If you're relying on solutions like HPA, HPA is definitely good. But what HPA does? HPA would wait for the microservice to hit the threshold. And instantly this service wouldn't hit the threshold because it would read the queue. It takes a lot of time to realize the queue is filled up. When I say a lot of time, it might take some 2 to 3 minutes, or maybe it might take some 1 to 2 minutes. And during that 1 to 2 minutes, there would be a bad user experience. From 20 to 30, 30 to 40, 50, 60, and only when the threshold is hit, HPA would start scaling the microservice. This can be avoided if DevOps engineers go for KEDA as a solution. What KEDA does, as the name itself suggests, it is an event-driven approach. So KEDA does not rely on metrics like CPU. What it does, when you install KEDA on a Kubernetes cluster, there is a component of it called KEDA controller. What you can do, you can ask the controller to watch the queue. It can be the RabbitMQ, or it can be Apache Kafka, it can be Amazon SQS. It will start looking at the queue. You can configure the poll, watch every 5 seconds or watch every 2 seconds, just for example. So it will continuously look at the queue. By the time, Amazon launches the Cyber Week sale, flash sale at 6:06, the queue is filled up maybe at 6:07, and instantly within 5 seconds, KEDA realizes the queue is full and it would increase the pod count irrespectively. So if the queue is filled from 10 to 100, let's say initially the items in the queue are 10 and this goes to 100 or maybe 1000, depending upon the elements in the queue, KEDA would increase the pod count. If one orders microservice can handle 10 elements in the queue, and if the order goes to 1000, so there is 100 times multiple. So KEDA would increase the pod count to 100. And the best part about KEDA, what it can also do, it can bring your pod count to 0 as well. So this is the second drawback of HPA that I was talking about. Maybe 2 a.m. in the night, there is no sale, there is no flash sale that is going on, and the items in the orders microservice, let's say, are 0. Hypothetical situation. What KEDA does, it can bring your orders microservice count to 0, the pod count to 0. And whenever there is even one element in the queue, it will watch the queue, so it can bring the pod count to 1. For the 2 minutes, for the 3 minutes, or maybe 2 to 3 hours, your compute cost is saved. You might feel it is very less time, but imagine 1 day, 1 month, 1 year, 10 years down the line, how much compute cost is your KEDA saving for you? Huge, right? I'll repeat this one more time. There are 2 advantages with KEDA, right? These are 2 major advantages. One, KEDA is completely event driven. It does not rely on the traditional metrics like CPU, memory, or metrics from your Prometheus. What it does, it will watch the queue. Like the queue like Apache Kafka, RabbitMQ, or Amazon SQS. Whenever there are elements in the queue, irrespective of what is your status of the pod, your pod might be at 2% CPU utilization. It doesn't care. It would look at the elements. If the elements in the queue goes to 1000, and if one pod can handle 10 elements in the queue, it would increase the pod count to 100. Whereas with HPA, it will see the CPU utilization. Okay, it is only 2%. Let me wait. It will wait for the CPU utilization to go to 80, which might take a couple of minutes of time. And then HPA would increase the pod count. So KEDA would save that time for you. And it is not about the time, it is not about the money, but it is about the user experience. Imagine Hotstar going down when Virat Kohli walks in, or some users cannot experience that thing. Or maybe imagine the Game of Thrones, all of a sudden, HBO sees a lot of users, everybody is placed in the queue, for example. So during the 2 to 3 minutes, you don't want your users to wait. KEDA can help you with it. Another thing, not only this, KEDA can also scale your pods to 0. At 2 a.m. in the night, nobody might be watching HBO. Just as an example, right? What? Or nobody might be using some microservices of HBO. KEDA can bring those microservices to 0. And as soon as one user or even there is some attention to that microservice, KEDA can scale it to 1. Whereas HPA can, the minimum that it can do, it can scale your pod size to 0, the replica count to 1. Whereas KEDA can go up to the replica count of 0 as well. These are two major advantages. Now, but Abhishek, can KEDA only work on event-driven architecture? That is, it can only act upon the queue? No, you can also use Cron. That is, you can also use scheduling. So you can tell KEDA, unlike HPA, you can tell it that every day, 6 a.m. in the morning, make the pod count to 1. Every day, between 6 a.m. and 10 p.m. in the night, keep the pod count to 10. Rest of the times, keep the pod count to 2 only. So you can also use the cron or scheduling with KEDA. Another big advantage, right? So most of the times, typical government platforms, the working hours of these government platforms, it can be 9 a.m. in the morning to 6 p.m. in the evening. During these hours, you want or you expect heavy traffic. Rest of the time, you might not even expect traffic to the government portals. So KEDA can work with cron or scheduling on such kind of platforms. Now let's see KEDA in action. Okay, we discussed a lot about it. Now let's see how this would work through a couple of demonstrations. So the first example, I will show you with cron. So I'll take a particular timestamp and I'll show you how you can configure the pod scheduling during it. And second, we will take a simple RabbitMQ example, the same example. Now we will take e-commerce platform like thing where there is a producer, where there is a consumer, right? And we will see how exactly it works. Yeah, you don't have to worry at all. Everything is in this GitHub repository. As I told you at the beginning of the video, the link is in the description. It has the complete notes, probably better than what I explained in the video. And it also has the demos. So we are starting with this demo 1, that is for the cron job. But before that, we need a Kubernetes cluster. Let's spin up a Kubernetes cluster. I clone the repository here and let me use kind create cluster. Let me call this as demo KEDA. My bad. Hyphen name demo KEDA. Okay. This would give us a Kubernetes cluster typically in 1 to 2 minutes. And to run kind, again, the steps are here. If you are new to kind, you need Docker, you need to install kind. That is also something that I've documented. Okay, now we have the kind Kubernetes cluster. Just clone the GitHub repository and switch to demo 1 cron. So here I have a deployment file. Within the deployment file, I have the deployment configuration, a simple Nginx configuration. I'll show you how you can scale up the Nginx and scale down the Nginx depending upon the cron. And that configuration I've defined in the scaled object.yaml. This is a custom resource that you have to follow. How do you use scaling with KEDA? You have to define the scaled object. So within the scaled object, I've defined the spec. So I explained within the spec, minimum replica count as 0, maximum replica count as 10. And this is the trigger point. What is the type of the trigger? Cron. If your type of trigger is different, just change this particular part. And I've defined the cron configuration. Time zone is Asia, Kolkata. This is the time zone that I'm in. If you want, you can change it as well. Starting from 9 a.m. in the morning to the 18, which is 6 p.m. in the evening, the desired replicas have to be 5. Right? Rest of the time, it's up to KEDA to decide how many pods are required. But during this time, I want the pods to be 5. Now, if you see, right now, it's almost 8 p.m. in the evening for me. So this cron wouldn't work. So what I'm going to do, I'll simply change this. Okay, let me change this to 22. Perfect. A very simple change. So now I'm saying from 9 a.m. in the morning to 10 p.m. in the evening. Now let's deploy both of these manifests. kubectl apply -f deployment.yaml. Right now, let's see what is the pod count. kubectl get pods. There are no resources. Okay. Now let's do this. kubectl apply -f followed by what is the name of it? Scaled object.yaml. Before, why there are no resources? If you look at the deployment manifest, right? This is the deployment manifest. I've defined the replicas as 0 because I want KEDA to take care of my replicas. Now, once I deploy the scaled object.yaml, KEDA controller comes into picture. But Abhishek, you did not deploy the KEDA controller. Yes, that is a prerequisite that we have to take care of. So how do we deploy the KEDA controller? I've documented the steps. First, we need the Helm chart for it. Let me quickly pull the steps. So this is the first one. Helm repo add KEDA core. Okay, I already have the Helm repo. Then we need to run Helm install KEDA from the KEDA core chart that we are using. -fn namespace KEDA create namespace. This would take not more than 1 or 2 minutes. So we can use this command to verify kubectl get pods -n KEDA. Once all of these pods are in the running state, we will get started. But Abhishek, what different kinds of things that KEDA would install? Let's complete the demo. Then I'm also going to explain you the simple KEDA architecture. There are only 3 components in it: the KEDA operator, the metric server, and admission controller. I'll explain you how each of them works in detail. It's also interesting. Okay, looks like most of them are in the running state. I can see the operator is running. I can see the admission webhook as well. Yeah, so only the admission webhook, it has to get to the running state. It's fine. I think it should be done by now. Okay, we will proceed with installing it. kubectl apply -f scaled object.yaml. Okay, now the scaled object is also created. Let's verify the status. kubectl get scaled object. Perfect. So it is ready. You can see the ready as true. Now let's verify the pod count. kubectl get pods. There you go. So you can see here, when I do kubectl get pods, the Nginx pods are coming up. And now they are 5 in number. Okay, initially 4 pods have come up, but the desired count is 5. You can see right now the 5 pods are in the running state. Why? Because I have defined the trigger in scaled object.yaml. Although the Nginx deployment was 0. Let me quickly show you. Cat deployment.yaml. This is the Nginx deployment. The replica count is 0. But as we deployed the scaled object.yaml, we have defined the trigger as cron. And within the cron, we said from 9 a.m. in the morning to 10 p.m. in the night, the replica count has to be 5. Awesome. Now let's look at the other example. Okay. So we will go back and let's head to the demo 2, the RabbitMQ thing. Now, what are we going to do here? This is going to be slightly complex example. Of course, the execution is almost the same, but what we will do here, we will take the e-commerce platform example where we cannot simulate the we cannot get the real users. So what we are going to do, we will use a service called order publisher. So I've written this Python application using AI. What order publisher does, it will simulate fake orders for us. Okay. And then we have the order consumer. Basically the same thing, the orders microservice. So we will install order consumer, the orders microservice. We will install the order publisher. So this will simulate the fake orders. So this will create, let's say, 100 fake orders or 200 fake orders. And these orders would go to the RabbitMQ. And who would read the RabbitMQ? Orders consumer would read the RabbitMQ and the configured KEDA, right? It would also watch the queue and it would scale the order consumer. I know this is little complex. Let me explain one more time. Basically, we will use something called order consumer. This is our microservice. What this microservice does, it would read elements from the RabbitMQ. Okay, but we need orders in the RabbitMQ. So for that, using AI, I wrote a Python application. This is called order publisher. So this would create some fake orders and these fake orders would be added to the RabbitMQ. Now we will use KEDA and we will use the RabbitMQ as a trigger. So KEDA would notice elements in the queue and according to the elements in the queue, you would see it would scale up the consumer and as soon as the orders would go to 0, it would scale down the consumer to 0. By default, there will not be any elements in the RabbitMQ because I'll first not start the order publisher. So when we install order consumer for the first time, the pod count will be 0. As soon as I install the publisher and I run the publisher, it would create elements in the queue, the fake orders. You would see KEDA noticing it and KEDA scaling the order consumer to 1, 2, 3. And as soon as the order consumer starts processing the orders, again, you would see this to 3, 2, 1, 0. This is what is going to happen. Very interesting example, right? So for that, what I'm going to do, again, we have to install these services. I have the steps documented in the demonstration itself. Let's start with, or we will create a new Kubernetes cluster. So kind create cluster -- name demo KEDA 2. Okay, because it is kind, it is creating a Kubernetes cluster within a container. So it's not a big deal. I'm creating a new Kubernetes cluster. Now within this Kubernetes cluster, let's start with installing the RabbitMQ first. How do we do that? So we will just run this command kubectl apply-f RabbitMQ.yaml. If you want to watch what is within the RabbitMQ, you can go through the manifest. It's typically RabbitMQ example that I've taken from their documentation. The RabbitMQ image, the container port, and the default username and the password. Okay. The next thing, once we have the RabbitMQ, verify the RabbitMQ pods are running. Okay. One pod is running. We don't need multiple replicas of it. We are perfectly fine with it. Now, the next thing that we have to do is to install order consumer. How will we install order consumer? Again, this is a microservice. I wrote a Python microservice, the consumer.py. If you want, you can go through the source code. As DevOps engineer, you might not need it anyways. Now let's build this order microservice and let's load the image onto the kind Kubernetes cluster. Docker build order consumer latest. Okay, so it will create an image on my local machine and then into the kind Kubernetes cluster. Kind load Docker image order consumer. And what is the name of my Kubernetes cluster? I think it is demo KEDA 2. Let's try it. There you go. So now the consumer image is loaded onto the cluster. Let's install the consumer. How do we do that? kubectl apply-f consumer.yaml. I have already placed the manifest. Perfect. So now we have the consumer running here. We have the RabbitMQ also running here. What is the next step? The next step, we will install, if there is a secrets manifest, you can install the secrets manifest. But before that, what we are going to do, we will verify what is the status of the consumer. kubectl apply -f pods or kubectl get pods. That is better. Okay, Abhishek, consumer pods are 0. As I told you, within the consumer deployment, I wanted to show you this. My bad. Within the consumer deployment.yaml, I put the replica count as 0 because I don't want any of my pods are running when the RabbitMQ is in the stale state. There are no elements in the RabbitMQ. Now, finally, let's install the KEDA configuration. How do you do that? Again, kubectl apply -f. Just like we did before, use the scaled object.yaml. What is inside the scaled object.yaml? That is interesting to watch. Okay, I'll show you that there is some error here. RabbitMQ is not installed within this Kubernetes cluster. We did install it in the previous one. No problem. Let's install. So helm install KEDA, create a namespace. kubectl get pods -n KEDA. Okay, let's wait for it. In the meanwhile, let me show you the scaled object.yaml configuration. So this time it is little complex. Previously we just used cron, so it was straightforward. First, I am using a secret resource. Can you guess why are we using the secret resource? I'm sure you must have guessed it. We are using RabbitMQ. RabbitMQ comes with a username and password. So I'm using the secret resource and trigger authentication for RabbitMQ username and password. Same if you use Apache Kafka, you have to use the username and the password. The scaled object. This time what is the trigger? Trigger type is RabbitMQ. Previously the trigger type was cron. I'm just saying, just watch the queue length because that is a trigger, right? Whenever there is elements in the queue length, then it has to scale up, and whenever there are no elements in the queue, it has to scale down. Perfect. Now let's see if this is in the good state. KEDA pods are running. Not yet. The KEDA metrics API server is still in the wait state. We need that container to be running. There you go. Now let's install the scaled object as well. kubectl apply -f scaled object.yaml. Perfect. Oh, my bad. I did not start the publisher itself. Okay, we are looking for the consumer pods. We are seeing if RabbitMQ, the KEDA is going to scale the consumer pods, the order service. It will not yet because we haven't created the fake load, right? Fundamentally, the concept is that there should be fake orders in the queue. Only then KEDA would scale the consumer pods. So we will first create the fake load. How? Don't worry. I have that application created with the help of AI. So we just have to build the Docker file publisher. So this is the Docker file for publisher. This is the publisher.py source code. If you want to see how did I simulate the fake load, you can go through the publish.py. But right now, let's create the Docker image and load that image to the cluster. Demo -KEDA2. Perfect. Now I think this is going to be our final step. I'm sure about it. So let's run kubectl apply -f followed by publisher.yaml. Within this, I'm running the publisher pod. Now, if what we learned is right, and if KEDA works exactly, there you go. So the order consumer should start spinning up. And if you just do kubectl get pods, you can see multiple consumer pods coming up. You will see more consumer pods coming up as well. And as soon as the consumer pods start completing the queue, of course, whenever a consumer pod comes up, it will start reading the elements from the queue, processing, it performs the processing, and eventually the consumer pod should go to 0. We will see that as well. Now let's give it 2 minutes and you should see the order consumer pods scale up and scale down as well. Right now it is at the peak. The fake publisher here, it published a lot of items into the queue. So lot of consumer pods are created. And once these pods start working, the queue will become empty and then you will see all of these consumer pods going down. Let's see, or maybe let's give it, yeah, there you go. So terminating. The queue is empty. Now the order consumer pods are also going to be 0. One more time. Yeah, it's still in the terminating state, but eventually you will see them not in the terminating state, completely removed as well. What are in the running state? RabbitMQ is still running and order publisher or fake order script is completed. It's just a Kubernetes job. Yeah, there you go. So kubectl get pods, the consumer count is 0. Now finally, okay, now that we understood KEDA through examples, finally let's understand what are the different components of it. It will just 2 minutes to understand. The first component is the KEDA operator. You know what it does? It just looks at the queue and takes the necessary action. Apart from that, there is something called the metric server. This is the most important thing. And surprisingly, what this does, it makes use of HPA itself, right? So basically it exposes the metric. So it will just tell the HPA how many pods needs to be created. So KEDA does not do anything on its own. So it creates an HPA. So the metric server, it exposes the metric to the HPA. That is how HPA works, right? It relies on metrics and that metrics is provided by the metric server of KEDA. So if this tells 10 pods should be created, HPA is going to create 10 pods for it. And finally, there is something called admission webhook. If you're providing wrong configuration, or maybe you're creating 2 different scaled objects, then the admission webhook of KEDA would basically tell you, hey, you are creating a wrong configuration. These are 3 building blocks of KEDA: operator, metric server, and admission. The most interesting part is a metric server because a lot of people think KEDA is a replacement of HPA, but KEDA internally utilizes something HPA only. It internally utilizes horizontal pod autoscaler. But how it utilizes horizontal pod autoscaler is the interesting part. It exposes the pod metrics, how many pods are needed, and HPA would just react to it. Overall, what is KEDA? KEDA is a proactive approach. But what is HPA? HPA is a reactive approach. In most of the cases, HPA might work the best for you. But in extreme rare cases, where you are working with the, not extreme rare cases, but the rare cases where you are working with applications which has to be scaled in no time, or when you are working with sensitive applications with respect to scaling, then you might have to go with Kubernetes event-driven autoscaling, that is KEDA. I hope you found today's video informative. Everything is in this GitHub repository. The README file has all the manifests, it has all the steps that I've executed, the demo information. You just have to go through it, execute the steps, and master KEDA. Once again, if you have any questions, do let me know in the comment section. Thank you so much for watching the video. See you all in the next one.